when we're dealing with features that have different magnitudes, such as height and age, we normalize these features. So for example, our height may be 1.7, our age may be a value of 30, and if we visualize some of these combinations, then our distribution may look something like this. And to normalize this, we center the data around the mean and express how much the data points deviate from that in terms of the standard deviation. And so after that, the data may look like this. And now to give you some intuition for why the normalized data improves the model learning's capabilities, we again imagine a network with two parameters. And this time one parameter is connected to the height and one to the age. And if we now use unnormalized data, then a small change to our age weight will result in a big change to our loss surface, since the age has such a high magnitude. And so we can imagine the loss surface being something like this. So for the height, we need bigger changes, since the height value is of a lower magnitude. And for the age weight, a small change will already result in big changes. So just as a recap, these closer lines represent a steeper descent, and the more spaced out lines represent a more mellow descent. And now, while we could work with adaptive learning rates and traverse this not so smooth surface, it would be better if we had a smooth surface. And so we go to the normalized data. And so here our weights will have equal influence on the loss surface. And this gives us a smoother surface, which improves learning. The smoother surface also decreases the importance of the initial weights, because the descent, no matter we start, is fairly easy, unlike here. And now the idea is that if normalizing the input to the first layer improves learning, why don't we normalize the input to the other layers, so the previous activations? And that is exactly what batch normalization is about. Whenever we pass a batch through the network, we normalize not only the input, but also the activations after each layer. So that activation is normalized, that activation is normalized, and that one. And so each layer gets then a normalized input. And this gives us then a way smoother loss surface, improving the model's learning. In TensorFlow, we find the batch normalization under tf.keras.layers. So just like where we also find the dense layer. And just like for the dense layer, we can initialize a batch normalization layer in the model initialization function and then use it in the call, so in between various dense layers, or of course any other layers. But it is important that if we want multiple batch normalizations, then we also have to initialize multiple batch normalizations. And that is because we have two parameters which we are learning during training, and these parameters are the gamma and beta. And we can see here the gamma is scaling our data points and the beta is adding an offset. And so if we would reuse a layer, then we would also train only a single pair of parameters and not different parameters for different batch normalization layers. And so in practice, the beta will be a shift to our distribution, so either to the age or the height or both. And the gamma will add a scaling to either height, age or both. And we add these trainable parameters to not restrict our model in any way. So if it wants the activations to have a certain distribution, it can with these parameters.